and it's multiple layers or multiple strata. So today we're going to move on and we're going to talk about the dermis. But first, okay, we're going to do a question. Okay, I think we are. There we go. So, which of the following is a function that's associated with skin? So we talked last time about all the different functions of the skin. Okay, that's my timer's not running and my mouse has disappeared. There we go. And this is a good example of a question that you should read carefully because, read the whole answer, in other words. All right, looks like we stopped getting new answers. Okay, so which of these is actually a function of the skin? That's going to be D, which most of you got. So protection against ultraviolet radiation. If we didn't have the stratum corneum, which is all that keratin that we learned sits on top of the epidermis, ultraviolet radiation would severely damage the DNA in our underlying cells. So one of the reasons we have that keratin shell is to prevent UV radiation from getting through to the living cells underneath. These others, fat production, no. The skin itself doesn't produce fat. The fat is produced underneath in the hypodermal layer. And it's not vitamin C, it's vitamin D. Vitamin D is the sunlight vitamin. We create vitamin D with exposure to sun. It's not regulation of body pH, it's temperature. So the skin is a primary player in thermoregulation or temperature regulation. And then it's vitamin D, not vitamin A. All right. So which layer of the epidermis is the one that undergoes mitosis to make new cells? All right, 5 seconds, so jump in there if you haven't already. 1, 0. All right. So the first layer, or the lowest layer, the layer closest to the underlying dermis, that's where the mitosis is happening. So new cells are being formed, and that's in the stratum basale. So basale means base or basal layer, so it's the lowest layer. It's the base of the epidermis, so we call it the stratum basale. The stratum lucidum is the layer that's found only in thick skin, and it's clear. The stratum granulosum sits just above the stratum spinosum, and then the stratum cornea is where, or corneum is where all those packed dead cells are, so the topmost layer. And stratum dermum, that one's just made up. All right. So which of these layers is found only in thick skin? Let's see if you were paying attention. What I just said. It's worthwhile learning those layers of the epidermis. There's only 5, and, they're easy questions to get right if you have spent just, some time learning all 5 and their order. All right, jump in there, last few people. All right, so the one that's found only in thick skin, that's D, the stratum lucidum. Now, it's not really, you'd think that this stratum lucidum would be what would make thick skin thick, but it's not. The difference between thick and thin skin is really the size or the depth of that stratum corneum on the top. Thick skin has a lot more stratum corneum than thin skin does. However, there's also this extra layer, the stratum lucidum, that falls underneath that stratum corneum. All right. So in addition to providing protection, the epidermis is also the site where where skin gets its color. And the color of skin is dependent upon multiple different factors, but the two main pigments that determine what your skin color is going to be is keratin and melanin. So keratin, it has the word carrot in it, and carrots are, of course, orange. Well, it's because carrots and keratin, it's all the same thing. So this is kind of an orange-yellow pigment. It's what gives carrots its orange color. Keratin, while itself is not a vitamin, the body can convert it into vitamin A, and then vitamin A is a powerful antioxidant. Now, keratin ends up being deposited in the skin, and I've got a picture of a squash baby here later, but particularly kids that have very fair complexions, if they really like their orange vegetables, like when they're babies, they can actually get kind of an orange tinge to the skin. You can spot them in the grocery store every once in a while, but that's called keratinemia, and it's from this pigment. So anything that's orange or orangish yellow has a pigment in it that may get deposited in your skin. All right. But the one, of course, that's much more famous is melanin, and melanin comes in different colors. There's a brown, there's a yellow-brown, there's kind of an orangish melanin, and then there's a deep black, almost blue melanin. So the color of any one person's particular skin is brought about by the kind of melanin that they have and then its quantity. So melanin is produced by melanocytes, which I'll show you a picture of here in a minute, and then it's sort of injected into keratinocytes. But an important point is that pigmentation differences, in other words, how dark your skin is not about the number of melanocytes. Pretty much all human beings, except for albinos, have about the same number of melanocytes in their skin. So the difference in pigment has to do with how vigorous or how synthetic those melanocytes are. So people with dark skin, their melanocytes produce much more melanin, light skin less. But it's not the number of melanocytes, it's the production of melanin. So we produce melanin because it's a kind of a built-in sunscreen. Melanin absorbs UV radiation, and by doing so, it prevents it from that UV radiation from causing damage to the cells underneath. So the reason that we evolved a melanin system is sun protection. And as we all know, if you spend time out in the sun, your melanin production goes up. You tan. There again, it's not only sun protection, but it's adaptive. So the more time you spend in the sun, the more UV protection you end up with. All right. So here is, turn these lights or one of these off. There we go. So here's kind of what a melanocyte looks like. All right. So we're way down. Here is our dermis down here, right? And here's our epidermis on top. That stratum basale is right here, right? That's where the cells are dividing. Well, sharing that strata with the keratinocytes of that stratum basale are these giant cells that we call melanocytes. So the melanocytes, they look a little bit like, the blob, so to speak, because they have all these feet that stick out and around. But melanin is produced here in the melanocytes, and then it has these long, slender processes that kind of reach out like an octopus into the surrounding keratinocytes. And the melanin that is produced here is then injected or placed into the keratinocytes that are all around here. So this melanin is produced here, but then it ends up in the keratinocytes. And remember, as these cells divide, these cells are always being pushed up towards the surface, right? So the melanin gets put in down here at the bottom, but then by the time those keratinocytes get to the surface, they still have that melanin in them. So, the whatever color melanin you have is produced down low and then sort of pushed up high. The packets of melanin that the melanocytes produce are called melanosomes. So a melanosome is just a packet or a bubble of melanin that's on its way into a keratinocyte to provide that color. So there's other colors that play a role in, when we look at a person, what determines that color that we see. This is my squash baby here. You can see how the skin is kind of orangish yellow. That's keratinemia, and that's from a diet that's rich in keratin, particularly with a very fair-skinned infant. Infant skin is very thin compared to adult skin, so you see coloration changes much more profoundly. Other things that give us our normal color, hemoglobin plays a major role. Hemoglobin is the protein that's found in blood that carries oxygen around, and it is colored. When there's oxygen attached to that hemoglobin, hemoglobin has a very bright red color. When oxygen is not attached, it has kind of a bluish color instead. So when we look at our veins, the reason that we see blue is because that deoxygenated hemoglobin has that kind of blue tinge. But, when we cut ourselves, blood is red because as soon as that blood emerges from the vessel, it's going to be saturated with oxygen because there's oxygen all around. So you never see, you never bleed blue, so to speak, because there's oxygen in the air around you. So that's hemoglobin. In this picture down here, you can sort of see how blue that is. That is deoxygenated hemoglobin, and this is it's called Raynaud's phenomenon. Some people, when their hands get cold, their fingertips turn blue because of vasoconstriction. This is an example of vitiligo, and the reason it's on there is it shows you what melanin does, essentially, because in these white areas here, there is no melanin production. It's an autoimmune disease, and that part's not important, but you can see the impact that the melanin pigment has on the color of skin. So there's no melanin here, and then we have normal coloration here. And then this one down here, this is jaundice. Oh, yes?
Are you born like that?
Like vitiligo? No. I mean, you can be born with spots that don't have melanin, but this particular disorder is one that develops over time. Yeah. But there are reverse birthmarks, though. Spots where melanin production just never happened.
Doesn't he get like one accent?
Oh, I don't know. I thought he did that to himself.
Yeah, I don't know.
Yeah. Was there another
He
question?
said it started like that.
Huh?
I said, supposedly he said it started like that.
Oh, yeah. Yeah. Who knows? Okay, so this one down here, this is not normal. You should not see people with these colorations. This is jaundice. Jaundice is a yellowing of the skin and particularly the whites of the eyes. So if you look at somebody's eyes and they're yellow like this, that's jaundice. It's the result of liver dysfunction usually, because the pigment bilirubin, which has kind of a yellow or yellowish green tinge, builds up in the patient's blood, and you see it in the eyes. Yeah.
So is that the same thing like if someone had cirrhosis of the liver?
Yes. Yes. You're going to likely see jaundice. Yep. Because the liver's job to get rid of that bilirubin. So when it's sick, it can't, and the levels build up, and they get yellow eyes. Yep. All right. Okay. So coloration. So far we've talked about the epidermis. So we're sort of starting at the outside, and we're working our way in. So the larger and in some ways more protective component of skin is the dermis. And we divide the dermis into two layers. So not 5 like the epidermis, but just 2. We have a papillary layer at the top. So this region right here is the papillary layer. And then underneath it, we have the reticular layer. So the papillary layer's job is really to provide and supply the epidermis on top of it. Because remember, the epidermis is an epithelium, and epithelia is avascular. In other words, it doesn't have arteries and veins. So in order to supply the nutrients and get rid of the waste products of the epidermis, we need to have a vascular supply. And that's what we have in the papillary layer. So this layer is very flexible. It's areolar tissue, which we talked about in the last chapter, which means that it's very loosely organized and it can move in all different kinds of directions. So in some ways, it gives the skin its flexibility that papillary layer does. We also find sensory neurons in this layer. We know that the skin is the largest sense organ that we have, and many of those sensors are found in the papillary layer just underneath the epidermis. All right. The reticular layer is a dense connective tissue layer, and this is where we find collagen fibers and elastic fibers. And those two fibers work together to give the skin both its rubberiness or its resistance to tearing or shearing, but it also gives the skin its flexibility and elastic nature. You can pull on skin and it'll snap back to its original shape. And that's the elastic fibers in the reticular layer that give it that property. And then the collagen gives it that firmness and resistance to stretching. So the reticular layer of the dermis. All right. So in that papillary layer, and to some extent in the reticular layer too, there are all different kinds of sensory receptors. And we're going to talk about those when we get to chapter 15, which is in our last unit. But for now, just know that there are multiple modalities of what we call touch. It's not as simple as we have touch receptors. We have light touch, fast pain, slow pain, vibration, pressure, temperature, in other words, hot and cold. So there's all different kinds of modalities or different things, different physical changes that the skin can sense. But for now, we're going to pick that up later and not talk about it right now. All right. Underneath the reticular layer is the subcutaneous layer, also called the hypodermal space. Here you're going to find adipose tissue, elastic fibers, larger arteries and veins that are going to supply the overlying skin. So we have a big artery here that's supplying not only the dermis, but then also the epidermis on top by going all the way up here and down. The subcutaneous layer is important because it allows the skin and whatever's underneath it to move separately. So if you think of the muscles of your upper arm, for example, as they move your arm around, they have to be able to move and twist and bend. Well, you wouldn't want your skin to move with the muscles underneath them, or you'd have puckering and twisting all the time. That'd be very uncomfortable. So the subcutaneous layer, because it's so loose, it means that the stuff underneath can move separately from the dermis and epidermis that are above it. So we use hypodermic needles will deliver medicine to this space, and it's a good place to put medicine because there's a rich vascular supply there, so that medicine gets taken up by the arteries and veins, particularly by the veins there, and then is distributed around the whole body. And then if you've ever heard of liposuction, liposuction pulls adipose tissue out of this space because this is the primary fat storage space in the body, is underneath the dermis, but on top of everything else. So like when we get into the cadaver lab again, not probably this week, but in the future, I'll try to show you that subcutaneous space where that's where fat is stored, underneath the skin but above everything else. All right. So the fibers that give the dermis, in particular, its strength, they run in a pattern. So the elastic fibers and collagen fibers, they don't just go every which way. They kind of run in parallel. And what this diagram is showing you, here's the front of the person, here's the back, is the direction of those fibers, how they run. So like here in the abdominal wall, they have kind of an angle toward an angle down, for example. When you get to the hands and arms, it can get very complicated. You can see there's a lot of different patterns here. But the reason I bring up lines of cleavage is when skin is cut parallel to these lines, it separates very easily and it heals very easily. In other words, it kind of wants to come back together if you cut parallel to these lines. If you cut perpendicular to these lines, the skin has a tendency to gape, or it holds itself open. So all that to say, when you look at surgical incisions, almost always you're going to see that they're going to be parallel to these lines of cleavage. So, like if anybody's ever had an appendix removed, chances are your incision is kind of at an angle like this on this side. And the reason for that is that's along with the lines of cleavage. If the surgeon cuts like that, it will heal much faster and with very little scarring. If, on the other hand, you cut perpendicular to these, it's going to take a longer to heal and likely is going to result in scarring. So there again, when they do a cesarean section, the line is usually a little bit like this, and it's, again, trying to follow those lines of cleavage. Particularly in abdominal surgery, you'll see that. So the reason that they cut at an angle is not because they missed or something like that. It's instead they're following these lines of cleavage. All right. Don't feel like you have to memorize this diagram. No. It's just kind of the idea. Okay, so melanin is produced where? All right, you made short work of that one. All right, so the correct answer there is D, melanocytes. Now, of course, that seems like a very simple question, right? But the reason I put it in there is don't think that keratinocytes produce melanin. And it can be a little confusing because keratinocytes contain melanin. The stratum corneum, which is the surface of the skin, obviously has a color, but that melanin didn't come from the keratinocyte. It can't make melanin. So instead, its melanocytes produce melanin and then put them in the keratinocytes in those melanosomes. Langerhans cells are actually immune cells that are found in the epidermis. We talked briefly about that last time. And then Merkel cells are cells that sense pressure. All right. So the dermal layer closest to the epidermis is which of those things? All right, 10 seconds. Jump in there if you haven't already. All right, so the epidermis is on top, right? And the layer right underneath that epidermis, that is the papillary layer of the dermis. And then deep to the papillary layer is the reticular layer where we find those elastic fibers and collagen fibers. All right. So far on our integumentary systems chapter, we have been talking about the cutaneous membrane, which is the fancy name for skin. So in addition to the cutaneous membrane, which is made up of the epidermis on top and the dermis underneath, also included in this system are what we call the accessory structures of the integumentary system, particularly hair, glands, which are going to be the various sweat glands, and then nails. So we're going to sort of talk about each of those in turn. Okay. So hair has multiple functions. The body isn't going to make anything that doesn't have a purpose or a reason. We probably, as humans, kept, we maintained hair on our head even though we lost most of the hair on the rest of us, in part for UV protection. As animals that walk upright, if we didn't have hair in our head, the sun would make a major impact on the skin of the head, and also probably create a heat problem too, because the brain is sort of a high temperature organ. So it's UV protection. Insulation, there again, hair on the head is like a stocking cap all the time. It helps to keep the heat in. Although the hair on the rest of us probably doesn't do very much in terms of that anymore. We have hair in particular places and particular kind of hair as a way to prevent the entry of foreign particles. So, you have hair in the openings of your nose, in the openings of your ear, and around your eyes. And in all of those places, it's to keep stuff out. So, those hairs, even though they can be, troublesome, they keep bugs from getting in there. They keep, dust and stuff like that out of the various orifices of the body. The eyebrows in particular probably evolved to protect the eyes from not only sun, as a little bit of a sun visor, but also sweat, so that, as sweat comes down from the forehead, most of it is caught by the eyebrows. And then hairs all over our skin, every single hair is innervated. In other words, it has a nerve attached to it. So it increases our skin's sensitivity to motion. Think, for example, a housefly lands on your skin. One of the ways you're aware of that is because it moves hairs as it, walks up your arm or whatever. And because those hairs are innervated, it sends a signal to the brain that, that you can swat it. Hair increases that as well. The anatomy of a hair follicle, we divide the hair up. The shaft of the hair is the part above the surface of the skin, and then the root of the hair is the part that is underneath the skin. And what's important to note here is, see this? This is the epidermal layer right here, and this is the dermal layer. So hairs go very down deep into the dermal layer compared to the epidermis. And you can see that the epidermis kind of follows the hair down as well. So the hair is actually a product of the epidermis, but it's found way down deep in the dermal layer. Okay. Okay. Associated with most hairs, anyway, is a gland called a sebaceous gland. So we can see this is a simple branched duct here. And these glands produce sebum, which we're going to talk more about here in a minute. The hair bulb is down here. So this whole area here is the hair bulb, and it's the place where the hair is actually produced. The hair matrix is right here. This is the area of cell division. So just like the stratum basale is where cells divide to produce the cells of the keratinocytes of the skin, that same process is happening here at the hair matrix. So cells are dividing, and then they die, and then those dead cells actually become the hair itself. So essentially, a hair is a secretion. It's non-living, but instead of like sweat is a liquid, hair happens to be solid and has a solid structure. So the hair matrix is where the cell division is happening. Supplying that matrix with blood is the papilla. So here's the hair matrix. It has kind of a cone shape. Underneath it is the papilla. And then all hairs have a muscle associated with them called the erector pili muscles. And when this muscle contracts, what it does is it pulls the base of the hair up to 90 degrees. So it sort of tugs on the base of that hair. Usually hairs grow at kind of an angle, so they lay flat. When the erector pili muscle contracts, those hairs stand up because the root of that hair is essentially pulled. You can imagine if this muscle contracted, this part of the hair would go this way, and by doing so, the top of the hair would then stand up. So that's the goosebump muscle. So the color of hair is primarily determined by melanin again. Melanin is produced and put in at the hair matrix, so it's produced by melanocytes again, and kind of injected into the keratinocytes that create the hair. And then if we look at a hair in cross-section, we can see that it has this very careful structure. It has the outermost, it has a connective tissue sheath, and then multiple layers, which you don't need to know the layers of hair. It's not that important. All right. So hairs don't grow all the time. They grow for many years, and then they stop growing. It's like they take a rest. So for 2 to 5 years in the active phase, the hair matrix is seeing cell division, and this hair is getting longer all the time. And then after that amount of time, the follicle becomes dormant. So what happens is the hair matrix and hair bulb kind of go away. They involute, or they disappear. Once that happens, there's nothing holding this hair into the body anymore. So we call that a club hair. And these are the hairs you lose, from your head and from your skin, that they're coming from follicles that are in the resting phase. So at some point, this hair will be let go, and it'll fall out. We'll shed it. And then eventually, that follicle will then become active again and produce a new hair to replace it. So because we have so many of these hair follicles on our head, for example, you don't notice when any one follicle goes dormant. You just find a hair in your hairbrush. But then as soon as one is going dormant, usually another is waking back up. So we keep about the same amount of hair all the time, at least until you get into things like male pattern baldness and stuff like that. All right. So that's hair, one of the accessory structures. We have glands. We have sweat glands and sebaceous glands. So many sebaceous glands are associated with hair, like a hair follicle like we've seen before. But some do open directly onto the surface of the skin. Sebaceous glands create sebum, and sebum is a very oily substance. Essentially, it's our built-in leather oil system. If any of you have had leather shoes or leather coat or whatever, you have to take care of the leather and give it kind of an oiling to keep it nice and soft and supple. And for the body, that's what sebum does, is it keeps the skin from becoming dry and brittle. So it's an oily, lipid-rich substance. It's produced in these glands, and then it's excreted onto the surface of the skin, where it sort of flows out very slowly. They're associated with hairs because hair will get very dry and brittle without sebum. So if you want to compare it to conditioner that you'd use to take care of your hair, it's sort of our built-in conditioning system. Sebum is produced down in the follicle, but then it takes care of this hair that's above it. All right. Then we have two kinds of sweat glands. We have apocrine sweat glands and merocrine sweat glands. So when you think sweat glands, what you're thinking of is merocrine. The sweat glands that produce thin, watery solution that's produced when we get hot or when we're exercising or whatever. So those are your merocrine glands. They're found in most areas of the skin, and they produce that watery solution. Now, the purpose of merocrine sweat glands is thermoregulation. If we put a little water on the skin, when that water evaporates, it takes heat away with it. So it's one of the thermal regulators of the body, are these merocrine sweat glands. And then in addition, there's also some antibacterial action as well. It's not just salt and water like we think of. Sweat also has some other substances in it that help to reduce bacterial load on the skin. So it is antibacterial. Now, the other kind of sweat glands, the apocrine sweat glands, current best thinking is these are our scent glands. You've all learned in biology that many mammals use scent to communicate. Well, the apocrine sweat glands are probably the human version of that. They are not found everywhere. They're only found in the axilla, the groin, and around the nipples. The secretion that they make is much different than the merocrine sweat gland. The merocrine is watery and salty. Here we have a very viscous or thick secretion, and it's very complex. There's lipids in it, there's carbohydrates in it, there's all kinds of stuff in apocrine sweat glands. Now, the problem is all that complex secretion is food for bacteria. So the reason why body odor exists is not because of these merocrine sweat glands. It's the apocrine sweat glands. They produce a substance that bacteria break down, and then those breakdown products have a smell. The apocrine sweat glands don't start producing anything until after puberty as well. So these are on when you're born. These don't develop until later. All right. So apocrine and merocrine. Okay. Then the last of the accessory structures is the nails. So nails, they protect the ends of your digits. The digits are our fancy word for fingers. And by the time you get to the end of the fingers, you have not very much tissue between outside and bone. So the nail evolved to help to protect the underlying bone from damage, because bone takes a lot longer to repair itself than skin does. So over the surface of the end of the finger, we have our nail, and it sits up just above the bone that is in that last phalanges. So if we look down deep, we'll see that the nail bed is what sits underneath the nail body. So this is the nail body, what we think of as our nail. Underneath it is the nail bed. And then if we look at it from the side, which is probably the best way to visualize, what's really going on there, is this nail. Okay, so this is the part we can see, right? But then the nail actually continues on down, and this is the nail root right here. And this is where the nail is actually produced. Nails and hair are really the same stuff. They're just put together differently. In the hair, we have this kind of concentric circles. In the nail, we have this kind of sheet that is being made all the time. So the cell division occurs down here at the nail root, and as it grows, the nail is pushed out this way. So the reason we have to clip our nails sometimes is because this process is ongoing. So we clip the end because the root is continuing to grow all the time. All right. Let's see. We covered everything. In case you didn't know, that little white moon shape at the bottom of your nail is called a lunula. So it's a great Scrabble word, lunula. Okay. The activity of apocrine sweat glands is to do which of those things? There. All right, jump in there. All right, so the correct answer there is B. Apocrine sweat glands are what lead to body odor. And the reason for that is what they produce is nutrient-rich, essentially, for bacteria. And then, so the bacteria break it down and it causes a smell. We didn't talk about the cerumen glands. Cerumen is earwax, and we'll talk more about it when we get to the ears. But essentially, it's not there by accident. Cerumen actually helps to keep the ear canal clean because it's produced way down deep in the ear canal, and it's always moving out. So one of the reasons why Q-tips are a bad idea is Q-tips have a tendency to push cerumen back in, and cerumen is supposed to come out, because when it comes out, it brings all the dust and debris and stuff that got down in the ear canal with it. C, gives the skin a healthy glow. Who knows? That sounds like an ad of some kind. Sweat on the palm of the hands, those are merocrine sweat glands. And the glands that produce an oily secretion, that's sebum, the sebaceous glands. All right. So as we age, skin changes. That one we all know. Wrinkles and differences in skin are one easy to see thing that changes with age. So what are those changes in reality? Fewer melanocytes. Fewer melanocytes means less melanin. People tend to get paler, in other words, as they get older, particularly as they get very high in age. The skin is very dry. If any of you have ever taken care of an elderly patient, that's profound. And we encourage our elderly patients to take good care of their skin, to use moisturizers and lotions and things like that. Because dry skin is brittle skin. So it breaks and breaks down much more easily. The reason for that dryness is the sebaceous glands don't work as well as you get older. So no sebum means dry, cracked skin. The epidermis itself gets thinner. There again, if you've ever taken care of an elderly patient, their skin can be like paper thin, and it can tear very easily. So that too is just a result of aging. A diminished immune response. The Langerhans cells that we talked about don't work as well as you get older. The dermis itself thins. So one of the reasons that the skin of an elderly person kind of sags a little is loss of dermis. Remember, the dermis gives the skin its rubberiness and elasticity. So we have less of those. I think it's on there, but there's also a decrease in elastic fibers. Where do wrinkles come from? As you get older, you have fewer and fewer elastic fibers. So just like an elastic waistband that's, been through a few, dozen washings or is a couple of years old, it doesn't quite snap back like it used to, and at some point it doesn't snap back at all. That's essentially what aging skin is doing, is the elastic nature of it has gone away, so it just kind of hangs instead of snapping back. The older you get, the fewer Virachron sweat glands you have that work. This plays a major role in the summertime when it's very hot, because the older you are, the less effective your sweat system is. So when we have these big heat waves and we hear about elderly people dying, this is one of the reasons for it. They are missing one of the cooling systems that we all use to stay cool when it's hot outside, and that's that perspiration and evaporation system. The blood supply to the skin is reduced as we get older, which makes the skin cooler, and this, just along with the sweat glands, means that the skin doesn't work as well as a radiator either. If there's less blood flowing to the skin, there's less ways to get rid of excess heat. So there again, in the summertime, the reason that elderly people sometimes get in trouble with the heat is that reduced blood supply means they got no radiator. So not only do they not have an air conditioner, skin or sweat evaporating, they also don't have a radiator to get that heat out there either. The skin is much slower to repair as we get older, and then there are fewer active hair follicles. So if you look at the hair distribution of somebody who's elderly, they have many fewer hairs on their skin surface than they did when they were younger. All right. This is just an example of a skin disorder. You can see those legs don't look quite right, huh? This is rickets. Rickets is a vitamin D deficiency that leads to a calcium deficiency. And essentially, instead of bones being rigid, when you get rickets, they get kind of flexible like rubber. So when a young person stands up, they bow out, like you see here. So this is a result of too little sunlight or not enough vitamin D, depending on how you look at it. We don't see rickets anymore because all of the milk that you buy in this country is vitamin D fortified. So we got rid of this one through that public health initiative. All right. And then the last thing we're going to talk about is one of the fanciest things that skin can do is heal itself. Imagine if that wasn't true. Every injury that you ever had would still be there. So just to sort of show you how that works here in our last few minutes. Here's an initial injury. So this is a cut, let's say, got cut on a piece of glass. So it's cut through the stratum corneum, which is right here, through the epidermis, which is here in blue, and then down deep into the dermis. So obviously the first thing that happens is bleeding. Because there's blood vessels in the dermis, some of those blood vessels are going to be cut open by this injury. So the blood flows into this little trough, into the injury there. And what you'll learn about next semester is blood clots. There's a system that turns liquid blood into a kind of mat or net of fibers. So we end up with our blood clot here. Now the bleeding has stopped. That's good. That's what the clotting system is there for. But, we have to repair this injury. Just leaving a blood clot there forever is not going to work because blood clots break down eventually. So after several hours, the clot, cells start to invade it. So cells from out here work their way into the clot. Those are macrophages. And they start the process of cleaning that clot up. And then you can also see here's the epidermis here. But even after a couple of hours, we have growth down the sides of it, right? So the stratum basale, which is right here and here, is dividing and creating cells that are going to reach underneath this clot as part of the repair process. All right. So after a week, we can see that the epidermis has kind of grown back underneath the clot. The clot has been replaced here with fibers. These are called fibroblasts. Those are cells that produce fibers. And they have replaced the clot with, usually it's collagen fibers. And then after several weeks, we see very little indication that there was ever a problem here, except we do see that, here's a little indentation, so it's not quite as flat as this. And then if we palpate this, if we feel this, we're going to feel those fibers or that kind of tough tissue underneath. And I know you've all had a wound that's healed, so you know what I'm talking about. Scar tissue doesn't feel the same as regular tissue does. And that's because it has much more collagen than elastin, which is what you find in the dermis. So it's a little harder and it's less stretchy. Now, over many months, this scar tissue often will be replaced by normal dermis, even to the point where you can't find where that injury was. So scars do sometimes entirely disappear. All right, we'll do one last question before we call it here. Eskimos wear a great deal of clothing and have limited exposure to UV light, but do not suffer from vitamin D deficiency. So make a guess as to why you think that might be here in our last minute together. Wow, good for you. Was this in your book? No? It's C. They get vitamin D in other ways. So there's more than one way to get vitamin D than making it in your skin. But it is true that they don't get enough sun exposure for that. All right, thank you, everybody. I'll see some of you in lab here in a little while. And the rest of you...